So this is the third question I promised my Year 12 students I'd do. We didn't get a chance to finish them last Friday, so I promised I'd put them on the channel so they can sort of check over the working. So it's another specific heat capacity question. We've got a jug of milk, 2 kilograms of milk. It's put in the refrigerator when it cools from 18 down to 3 over 100 minutes. And our specific capacity of milk is a little bit under that of water. So first we want to know the thermal energy removed from the milk as it cooled from 18 to 3. So the energy removed again, mass specific capacity, change in temperature. We've got 2 kilograms specific capacity of milk, 3,800 times by, put it as minus 15, that is the change in temperature, it's dropped to 15 degrees. So that's going to equal 114,000 joules of energy removed from the milk. Okay, so how much was removed? 114. The rate at which thermal energy was removed from the milk. So that's happened over a period of 100 minutes. So we want to know the rate per second. So we're just going to say here's our 114,000 joules divided by 100 times 60. That's 100 minutes. And that comes out as an answer of around 19 joules per second, or 19 watts. And then finally, we've got another container full of milk. It's placed in the freezer and cooled again, but this time it's cooled down to minus 18. So it's going to freeze. Assume the thermal energy is removed at a constant rate, and the freeze point of milk is around 0. The specific heat capacity of the milk below 0 is significantly less than its value above 0. So what does that mean? That means if you're taking energy out of the milk once it's frozen, it takes a less amount of energy per degree C that it drops for the same mass of milk. So it's going to cool quicker. Once you've frozen it, then the rate of temperature drop is going to be greater. And then it asks us to sketch a graph to show the variation of time of the temperature over that period, over that temperature range. So we're starting at 18, tells us this. It's going to cool down steadily. The specific heat capacity isn't changing, so it's going to be and the energy removal is constant, so that should be a straight line. For some period of time, we don't know, but for some period of time, it's going to freeze, and then the temperature is going to stay at 0 because it tells us that the temperature it freezes at is 0. And then once it's frozen, it's going to start cooling down again. But this is the key. We know it's got a smaller specific capacity, so we've got to put a gradient that is clearly steeper because it's cooling quicker. Okay, and it doesn't matter if this is a little bit shorter or this is a bit longer. The key points are you've got a straight line there that is dropping, then you've got another straight line at 0, and then you've got a third straight line where the gradient is greater here than it is here. And that's worth 3 points.